Hello, today I just wanted to give an overview of this terrain system that I created for Godot 4. I learned a lot in the making of this terrain system in this video, and I just kind of wanted to share everything I learned as well as release the terrain system I created for other people to use. So if you want to use it, it'll be linked in the description below, and I hope you enjoy the video and find it interesting. So it is a fully featured terrain system. We have proper normal mapping. We have an LOD system with different LODs which get less detailed as you go further away from the camera for performance, and they are cleanly stitched and blended together between LOD levels. It also has a fully featured editing system where you can paint on the Splatmap of the terrain. You can paint holes onto the terrain. You can raise and lower the terrain within the Godot editor. Flatten it. And collision maps are pre-generated in editor before running the game. And for all the foliage that I added to the terrain, I just used the wonderful Spatial Gardener extension, which is available for free, and I will link it below in the description. Now I've started a new project here, and it's actually very quick to get something that at least resembles terrain. So what I'm going to do is add a new mesh instance 3D to this brand new scene, and I will set it to use a plane mesh, and I'm just going to crank up the subdivisions so it has a bit more detail and vertices in the mesh, and I'm going to add a new shader material. And all materials in Godot use shaders under the hood, but this is just a material which allows us to directly modify the shader code, which is just code which runs on the GPU instead of the CPU, and allows you to do things like modify the vertices of the object, such as move them around, or modify the colors on the object. So you have very fine-grained control of how your object is going to look when you're using shaders. So first thing I'm going to do is change the render mode to wireframe and unshaded, just so we can see what's going on here. So as you can see, we have the subdivided plane mesh, and I'm actually going to go even higher than 7 subdivisions. Let's say 15, and I'm going to make it a little bit larger. So we have this large plane mesh with a bunch of vertices on it, and actually very quickly we can get something resembling terrain. So if I add a uniform sampler 2D parameter, and a uniform is just a parameter that is passed into the shader, so I'm going to call it heightmap. And then once you've added a shader parameter in Godot, it will give you an option to set it within the editor or the engine. So I'm going to add a new noise texture to that, and just add a new Perlin noise texture. So now that we have the noise texture, which Godot conveniently provides us this noise texture 2D class we can use anywhere a texture can be used, and we have it passed into our shader parameter and set as the heightmap parameter here, we can very quickly get something that looks like terrain by doing vertex.y plus equals texture heightmap vertex.xz .r. So because it's a black and white texture map, R, G, and B are all going to be the same value. It's just going to equate to the brightness value of the texture at any pixel. So just with that, we already have something that kind of looks like terrain here, and we can modulate how it looks a little bit by changing the noise that we're passing in, and already we got something that looks like terrain. And we can make it look even more like terrain by passing in an actual texture. And I'll call it terrain for now. And in the fragment shader, I will set the albedo color to so I will sample the terrain texture that we're passing in, and for now I'll use this grass texture, which is from cc0textures.com. And if I drop that into the terrain texture parameter that is now showing up on our shader inside the material, and I turn off wireframe mode, looks pretty distorted here, but you can see it's already looking quite a bit like terrain. The colors are not quite right, but it is indeed looking like terrain. I think one of the main reasons here is that it needs a source color hint. Yep, so this is already looking quite a lot like terrain, and we were able to get this up and running in just a few minutes. And what you've seen here is the basic premise of how I implemented the full terrain system over here. The difference being is that it's actually rendered as a bunch of different meshes. So each one of these meshes would be a plane mesh that I'm creating within the code, and I'm stitching many of them together. So the advantage of using multiple different plane meshes is that we can swap them out for different levels of detail. So as you can see on the very far LODs here, we only have 1, 2, 3, 4 subdivisions, while on the highest LOD, which you would see when you're directly on the ground, looking at the ground from the player's perspective, these have, I can't even count how many subdivisions those have, it's quite a lot, and it's much more efficient to render a lower level of detail further from the camera with less polygon and vertex counts. So to go the next level up in complexity from this simple single mesh terrain system, I've created this other scene here, which introduces a fraction of the code base for my main terrain system. And in this one, we have a chunking system. So instead of just having one mesh, we can have many of them being created to represent our terrain. And I've just discolored the odd chunks to show where the borders between the chunks are. And now the next thing I'm going to add to this to go up another level of complexity is an LOD system. So that just means to draw further away chunks on a lower subdivision mesh. And when we do this, we can actually just, if we have 5 different LODs, we can use the same 5 meshes and share them between all of the chunks. So that gives us an efficient way to do LODs. And in practice, if you set the drop-off rate of the LODs low enough, or low enough, it's not really going to be noticeable in game, and you're going to get a large boost in performance. Like, I have the frame counter up here. If I turn off LODs, you can see we're getting 1100 FPS, and just by turning it on, we get a 400 FPS or so boost now that we are rendering further away chunks at a lower resolution. So if we have the player's camera here, and by the way, the different colors are just, it's just swapping what color it is at every LOD change. They don't mean anything in particular. You can see the LODs are following the player around the map with the highest detail the closest to the player, and these level of details that are really far away, you can see these chunks, each chunk is a square in this context. These become such a low level of detail that it's just one single quad mesh. Now, this is all well and good, and this does work, but this introduces a little bit of a hairy problem. So if I turn off the debug draw of the terrain and zoom in, you may notice these kind of weird little gaps in between the mesh which follow the player. So if you notice, the gaps are happening at every change in LOD. If we take a closer look and examine two neighboring chunks of different LOD levels, it becomes a little bit more clear what's happening here. So we're going down LOD levels this way, and this chunk here has 3 vertices along its edge, while this chunk here has 5 along its edge. And there are some spots where they match up here and here because it is basically halving the amount of vertices, or close to, it's not exactly halving because it's halving the number of faces that it has. I think the number of vertices are halving plus 1 or something. But this pattern of how it goes down in vertices per LOD, or just the fact that lower LODs are going to have less vertices along the edge, introduces this problem where there's going to be these vertices here, which there just isn't a vertice on this chunk corresponding to the same one here. So if this is trying to represent the underlying height map, this chunk here is just not going to have as many vertices as this one, and it's never going to be able to represent the same level of detail at this point that this chunk is representing. These ones are matched up perfectly because they're sampling the height map at the exact same point, but because there is no vertice here to sample the height map on this one, we just can't do it. So the fix for this is going to be in the shader, and basically what we're going to do, if this is the level 4 LOD, higher is more detailed, and this is 3, in the shader, whenever we're at an edge of any chunk, we're going to pretend we're in one lower chunk or one lower LOD. And so instead of sampling at level 4 granularity, we're going to sample as if we were at level 3 and we could only take these 2 points here. And instead of sampling the true value of the height map here, we're just going to sample these 2 points and then interpolate between them based on where in space we are. So this point right here should be half of the height between these two, which is what this exact, there's not a vertice here on the other side, but this point, because it's like a line drawn between these 2 vertices on the edge of the chunk, this would be half of the height between these 2 neighboring vertices. So when we're on the edge of a chunk, we'll just pretend like we're in the neighboring one, and then that's going to give us the correct height value for that vertice. And then I just have this bit of code here to do the interpolation between the lower resolution of vertices. So we have 2 vertices here and 3 here. So when this one is snapped down to a lower LOD, it's really not going to make any difference because this one already has a vertex there. And same with this one. When this one snaps down to a lower LOD, there's no vertex here at this lower LOD. So basically what I do, you can see in the code here, we calculate the number of segments or vertices along the chunk. And so in this case, it is going to be, I think this is going down to 2, and then we can just calculate the exact position of where the vertice would be. So we have the position of this one here, and then we snap it down to this vertice here, and then we snap it up to this vertice here, and then the interpolation factor is going to be the x and y value here, and then based on the distance we mix or interpolate between the snap down and snap up of the two vertices on the lower LOD. And with that, you can see that it perfectly matches this vertex on the higher resolution to this lower resolution where there is no vertex. And by pretending we're in this lower LOD, it perfectly matches and stitches those little gaps within the terrain. And now our terrain is no longer going to have the problem of creating seams within itself. And you can still see the LODs switching as the player's moving away or the camera's moving away from chunks. And they won't notice from their perspective because the ones over here are not going to be clearly visible. So you can keep the higher resolution near them and the lower resolution away from them. Now this is the finalized version of the terrain, and one additional feature I had to add was setting the normals by hand. So if I turn that off in the shader, you'll see we just have this totally blank, flat looking terrain that doesn't even really look like terrain much anymore. And the reasoning for this is because it's still a flat plane mesh underlying it. Even though we are modifying the height in the vertex shader, it does not carry over the normals. So it still has the normals, which are just vectors of length 1 that are pointing directly out of the mesh, and these are used to calculate lighting. So if it just has these completely vertical normals, which are only really going to be correct for a plane, when a terrain should have normals all over the place like this because it's all rocky and hilly. So to be able to use this efficient technique of having a bunch of chunks which are each their own mesh and swapping their LODs and all that, and being able to do it efficiently, we're actually going to have to recalculate the normals by hand instead of getting it for free basically with the pre-calculated mesh. So if I go back into the debug view here, let's see if we can take a bit of a closer look at some of these faces and see if we can figure out what the normals might be if we had to work backwards and do it by hand. So if we're looking at this face here, we have 4 vertices. Actually there's 2 faces, but I'm just going to do it per quad for simplicity. So normally each face is going to have a normal, and to calculate that, we only have the information of the height map at these 4 points. And we also have their x and z values. So we have the x, y, and z values of these points. And the way I'm going to calculate that here is, so if we take this point here subtracted by this point here, we are going to get this vector going this way. Hopefully that makes sense. If you subtract one point from another, that's going to make it give its position relative to that point, which would be represented by kind of this vector or arrow facing that way. And we can do the same thing over here. If we subtract this point by this point, that is going to give us the vector facing this way. And now we have 2 vectors at a right angle of this face that it's on. And if we take the cross product of these two vectors, that is going to give us this vector, which is at a right angle. That's a little bit hard to see. This vector, which is at a right angle from both of them, and that is kind of our normal. That's basically our normal. Because it's a quad, that is not exactly correct, but it's basically our normal. You could do the same thing with, you could go and get this and this, take the cross product of those, get this, do the same thing over here, get these two, and then get that cross product, and that would give you the exact normals of those two triangles. But in practice, I don't really think it's worth it, because the one normal and treating it as a quad is going to be a pretty good approximation for most cases, and it's going to take twice as much power to compute and store a huge normal map, depending on how big your terrain is, for potentially little or no visual improvement. So for this case, I'm just gonna go with this method. So hopefully that makes sense. The cross product gives you a vector that is perpendicular to two vectors, and if we go and normalize these two vectors and then take the cross product of them, that is going to give us the normal here. And how I actually do this in code is that I bake the normal map once at the beginning of the scene load. And so how this is done in code is basically just how I explained it visually, but done in code. And I'm pretty much just computing this in a separate shader, and I'm using the GPU to compute all the values for me with the strategy that I just mentioned. And we're just rendering to like an invisible quad, or in this case a texture rect, on a sub viewport that's not visible to the user. And so that'll take care of the normals for the shape of the terrain itself, but often we're going to be using textures which have normals as well. And you can see, like on this rocky texture, that has its own normal which interacts with light in a specific way to give it a more realistic look. And yeah, things are going to get a little bit more interesting when we have to combine the normals of the terrain with the normals of each texture. Normally the game engine would do this for us, but since we're doing this funky activity of deforming the mesh and creating the normal map ourselves from the original plane mesh, we're also going to have to do that manually and write out the logic for how that would normally be done. So here I just have a plane mesh with a rocky texture and its corresponding normal map applied, and hopefully you can kind of see what's happening here. I think it's pretty intuitive as to how the normal would combine with the normal of the plane. It's basically just going to rotate along with it in sync, how you would expect. That's what allows it to give that impression that there's kind of a bumpy surface that is, physically there on the terrain. So I made this little demo here to hopefully make it a little bit more clear, but like we have our plane mesh here, and those would be all our normals coming out of it. Like if there are rocks or whatever, they would be facing all different directions to kind of simulate the rocky or jagged surface that the texture is representing. And you can see when we rotate this, it would just rotate along with the plane wherever it's facing. The normals would just be always the same, but just relative to the plane. So if we view this problem slightly differently, if we simplify it a bit, it's not a bunch of normals. It's this one point that is going to be rotating relative to the plane. Like we see here, if we're looking at this grid, if we trust these grid lines as being one by one, you see this is 2x and y1. So the point's position is 2x and or 2 and 1. Usually you would say x, y, so 2, 1 is its position. Now if we rotate it, it's really anyone's guess where it's at. So here it's like 2 something, negative 0.2, something like that. So it's kind of anyone's guess where it would be when we rotate it, but it's still kind of at 2, 1 in a way, but it's just on this other grid. So relative to the plane, it's always going to be at its original position of 2 and 1. So I think that gives us a pretty good clue of how we might be able to find this point. So one way that I can think of to find it is if we knew these two vectors here. So if we knew the y-axis on this grid and the x-axis, so we could use those to extrapolate out the position of the point. And we actually do know the y-axis. That's just going to be our normal. It's going to be our normal of the plane. And the x-axis, it's really just a normal rotated 90 degrees. So we have these two unit vectors of the x and y on this plane already. It's just going to be our normal and our normal rotated 90 degrees. And if you think about it, we can kind of position this point. Like if it's on these grid lines positioned cleanly, we can think about it in relation to these grid lines. So it would be 2x plus y1. So it would be 2 in the x direction of whatever this grid is plus y plus 1 in the y direction. And this would just be equivalent to 2x plus 1y. And because we have the actual x and y values of these two values, we have the normal, which would be right here in relation to the origin, and then we have its 90-degree rotation, which would be right here. We can use those to find the position of the point. So just as an exercise, we have this position right here, and if we are thinking about it in terms of these two axes, so it's going to be 2x plus y1, and then we have the x and y values here. So we can calculate it by hand. It would be 0.8, negative 0.6 times 2, and that equals what, 1.6 negative 1.2 plus 0.6 0.8 equals 2.2 and negative 0.4, it looks like. And if we look at where that point actually lies on the graph, or on the main graph, it's kind of hidden here. Hopefully you can see it. We have 1, 2, it's about, that looks like 2.2 to me, and then negative 0.4, it's a bit under halfway here. So we have this final value by adding or putting these two unit vectors end to end, and that way we can get our point. And yeah, if it's instead a normal vector instead of a point, the same concept applies. We're just finding it in this grid relative to the plane. remember, whenever we're rotating something 90 degrees on a 2D graph clockwise, it's really just swapping the x and y's and then negating the y. And in the code, it's pretty much the exact same process as I just described in 2D, but in 3D in the shader. So we have our apply normal basis shader function that takes two normal vectors. Normal 1, that's probably going to be the normal of your terrain, and then normal 2 is the normal that we are applying onto the first normal. So that would probably be your like rocky texture, your grass texture, whichever texture you're using. And yeah, just do the rotation 90 degrees right and then 90 degrees forward, and then that gives us the new vectors that we're using as the basis for the new graph. So I call this change of basis. And yeah, we just do this same idea, the right or the x times the x of the second normal that we are applying or making relative to the first normal. Same with y and same with z, and then that gives us a reoriented normal to the new basis, which will be relative to the first normal. Now, something pretty cool here that anyone watching might have already noticed if you know a little bit about math is that there is a mathematical name for the operation that we just did, and it's called a matrix multiplication. So if we go ahead and say new graph equals matrix 3 by 3 made up of the up, right, and forward vectors for that. Actually, I think it would be right, up, and forward because it's x, y, and z. This should actually give us the exact same result as if we are doing this right times up times forward thing. So if we do new graph times n2, you'll see that there's no actual change in the shader there. And just to show that it is actually doing something, yeah, so this is controlling the normals of the terrain mesh. And yeah, the reason that this works is because a matrix multiplication is defined as exactly this operation. So we're putting in the right, up, and forward, or the x, y, and z as the columns of the matrix, and here we're basically just doing the matrix multiplication by hand. And if you didn't know, this is kind of the intuition of how matrices work. You might have seen 3 Blue 1 Brown, which is another YouTuber who does really good math videos that you might want to check out if you think this is interesting. So to really hammer home this point about 3 by 3 matrices being used as the basis, as the transform for rotating or scaling points also it works for, I wanted to show one more example. So if we go back to this, and we're looking at this scenario again where we have this point that's being rotated relative to this plane. If we say rotate it here, and we take a look at the x and y basis vectors for this new graph, and if we go into Godot, I have the same setup here in Godot. I have the point with its position set to 2, 1, just like the graph. And now if we go and set the transform of the parent of this point that it's rotating in sync with, and now I've set it to the exact same values as we had on our graph. We had 0.8, negative 0.6 for the x basis, and 0.6, 0.8 for the y basis. and I've plugged those into the transform 3D basis, and you can see we get this point that falls at the exact same location as it was rotated on our example. Now, all that touches on something pretty fundamental to game engines and computer graphics in general, which is the use of matrices to represent spatial transformations in 2D or 3D in this way, and has this kind of intuitive visual understanding behind it. So hopefully that made sense. This was something I just learned recently that I thought was really cool. So hopefully at least one person blew their mind, because that definitely blew my mind the first time I saw that. It was actually in this function. I was writing this, and then I just realized, wait, isn't that the same as a matrix multiplication, which I had seen before? And then I was like, oh yeah, that's okay, that makes perfect sense now. So yeah, if you look on the documentation for Godot's Transform 3D, you'll see that it consists of a basis, which is the 3x3 matrix, and then its last column is just a vector 3, which is a translation. And the way the matrix multiplication works out is usually how it will work practically is it just ends up being something like this. So if we're multiplying by a vector 4, you can just make your vector 3 a vector 4 and just tack on a 1 on the end. And then the way the matrix multiplication will work out, just like this was the equivalent of a 3x3 matrix multiplication, this is the equivalent of a 3x4 matrix multiplication onto N2. And that is how Godot's Transform 3D works as well. The last element of the vec3, when you make it a vec4, would just become 1. So then you do x, y, z, and then the last component is just a 1 times whatever the fourth column in the Transform 3D is, which is the origin or the translation. So that means after the basis transform is done, which is scale and rotation, then you just add on whatever the translation is, and it's basically just a neat little trick on top of 3x3 matrices to also include translation within them by adding an extra column. One thing I did want to quickly mention is the swapping the x and y components for 90-degree rotation doesn't quite work in 3D, but it gives us a good enough approximation for what the two other basis vectors are going to be, so that is why I'm using it. So now that we have our normals, everything looks pretty good, but another thing we might want to add after that is something called triplanar texturing. So while the terrain looks pretty good over here, if we have something like a steep cliff, you get a situation like this where you can see the texture begins to look pretty distorted on the sides. Now, this is a pretty common problem in games. Here's an example from a MMO that I still play sometimes, and I used to play when I was younger, called Fly for Fun. And you can see in this area, the texture looks pretty good on this flat surface here. But over here on this cliff, you can see the texture is starting to get distorted when you get to these really steep areas. The textures just seem to get stretched over. You can see it a bit better here, and the reasoning for why this is happening is that the texture is just kind of applied vertically or kind of pasted down onto the terrain, and because it's just applied vertically, it gets stretched massively all the way down. So this is just like a 2x2, whatever size that is, a few feet wide, but it's massively far down. So the texture gets stretched that whole way, leading to that distorted look. Now we can remedy this by using something called triplanar texturing, and I can show you an example on this sphere here. And basically, as the name suggests, there's three planes which are projected with the texture onto the sphere, leading to this one. The texture is just like a square picture of a smiley face, but it is projected evenly on all angles. So here I have this pretty much the same exact thing within Blender to hopefully show you a bit more clearly how this is working. So literally there are essentially just 3 planes which get projected in this way onto the sphere. 3 different kind of angles that the texture is projected onto. And also it does it for these sides as well, but these are like the 3 directions, and it does both positive and negative on those directions. But you can see like it's still a totally flat image if it's pasted on, so it doesn't fully solve the problem of distortion, but it gives us 2 more planes which we can blend between, and you can also do a smooth blend between these, but this is the basic idea of how it works. So here's where in the code I do the texture triplanar, and basically all it's doing is taking the x, y, and z of the normal, and depending on which value is highest, that direction of the texture is going to be blended between. So we sample the texture 3 times, and the x, y, and z values of the normal, which would be the direction that it's pointing in, whichever is highest, that equivalent texture is going to get blended towards. And then if we turn it on, you can see that we get this nice triplanar effect where it looks nice from every angle, and even on a hill the texture is not going to become distorted, except maybe some distortion there. I think that's a normal map, but yeah, it's still not 100% perfect on like really sharp cliffs like this, but it is going to help distortion a lot. And so in terms of adding editor GUI features like this, I have this toolbar that has terrain editing brushes and whatnot, as well as the terrain settings. Godot actually fortunately makes that pretty easy to do. So the editor for Godot actually runs on the engine itself, which means it's going to be a unified system for designing UI and everything. So if you're designing UI in game, everything that you see within the editor is going to be accessible to you to use within game. So if you wanted, you could basically recreate anything you see in editor. And yeah, just to illustrate, I have created a little mirror of what you see over here in the scene editor. And you know, essentially any UI that you're going to do in game, any UI that you see in editor, all is going to be sharing the same Godot engine API, which makes things pretty convenient when you're doing stuff like plugins. So yeah, all the UI for the editor amounts to this one scene that contains all of the settings and the brush toolbar in it, and then I just link this up to some code for being able to paint on the terrain's height map and Splatmap via just plotting pixels based on the terrain brush. Most of the logic for editing the actual terrain I have encapsulated into this terrain brush decal class, which just extends a decal, which is a built-in thing in Godot, which allows you to get this effect of projecting a texture onto 3D objects. And yeah, essentially, you know, when it's painting, it will edit its simple terrain parent. There's a bunch of settings for like brush size, which will change the size of the underlying image, which is just a gradient texture, which is another built-in class in Godot. And I essentially just detect where it is on the terrain and then plot the pixels onto the underlying texture for the terrain, which would either be the height map or the Splatmap, which we're going to talk about next. And yeah, so the simple way the Splatmap works is, if you look over here, there are 4 colors on here: red, green, blue, and black. and based on the color, I can apply textures 1 through 4 onto the terrain. So as you can see, as I draw over here, the splat map is updating on the right. And the simple way that works in code is just like we're sampling the height map, I sample the color at the splat map. And then in the fragment shader, I do a texture sample 4 times. Red is going to be black is going to be the first texture, red the second, green the third, and blue is going to be the fourth. We sample the 4 textures as normal, and then we just multiply each of the 4 textures by their weights. So for instance, for the red texture, or for the mustache and hair I just drew on this guy, that portion of the image is entirely blue, so the first 3 are going to be weighted to 0, and the last one is going to be weighted to 1. And because we're just using an RGB image, that also blends smoothly between the 2 textures when it transitions from one color to the next. Since we're using a splat map, holes are pretty easy to add in the terrain just by painting a transparent texture onto the splat map image. And one thing to note is that instead of getting this like kind of smoothly blended hole, I specifically blend it only if the whole triangle is going to be fully transparent, and that is so we can get the collision map to match up exactly with it. Here is the code for creating the collision shape, and as you can see, it's basically just sampling the pixel, and ordinarily we just set the height map collision shape, which is a built-in thing in Godot. You can just use a height map collision shape, and I'm just setting it to the height of the height map. And for holes, you can just set the value of the collision shape's vertice to nan, not a number, and that allows us to create holes in the collision map. So yeah, that was the video, and I hope that was helpful to somebody. If you have any questions, please leave them in the comments. I guess probably the main target audience with this video is experimenting a bit in creating it. I was trying to do more of like a visually interesting video, but it ended up being just like a very technical explanation of what I did. I learned a lot when I was creating this, and probably the main goal that I was going for in creating this terrain editor was just creating like a simple modifiable terrain system, because I was originally creating it for my game, which had portals in it, and I added a bunch of custom stuff to accommodate for that, and it just ended up, I was modifying some existing terrain systems, and it just ended up being this huge amount of modifications I was doing. So I just ended up deciding to write my own, and I think what I came up with is a pretty simple solution, and I hope it is useful to somebody. If you have any questions, or if you're interested in modifying it at all, please ask me in the comments below. If you're doing anything similar, hopefully I could maybe help you. If you ask in a comment below if you need any advice for implementing terrain or modifying my terrain system, or if you're just using it in your game, definitely just ask me below. I'll help with whatever I can. And yeah, that's the video. Hopefully it was useful to somebody. I guess it was mostly the story of just me learning a bunch of stuff in the process of creating this. I had a lot of fun doing it, so hope at least somebody found the video useful, and yeah, thanks for watching.